Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are at lecture 38 today and we are discussing about the crossover from DMT to JKR model as proposed by Moses, and we discussed this particular the curve plot in the last class in which the contact radius, dimensionless contact radius. So, we discussed about this particular plot in the last lecture, in which this is a dimensionless radius of contact, okay. In the y axis and the x axis there is dimensionless load, and this particular curve is for the Hertz mechanics and then the DMT and then JKR, and Moses he assumed this Dugdale model, and that this is the Dugdale model I discussed in the last class, by considering that the adhesion between this sphere and this surface, okay, within this distance, let us say delta c, okay, the delta c is not this one, delta c is this one. Now, within this distance delta c, the force is constant, that is sigma 0, that is Dugdale model. So, Moses used this Dugdale model, okay, to derive the expression for or the relation between A and P, and then made these plots, dimensionless plots, which is very helpful, we will see that. And this is based on this particular quantity lambda, that is the Moses number or Moses quantity, whatever you say. So, this is the dimensionless quantity where sigma 0 is that critical stress at the surface at the interface, and W is the work of adhesion, and capital K we know that is this 4 into E star by 3, right. So, that is a measure of this Young's modulus of this material, and E star is of course this effective elastic modulus, and capital R, that actually is the relative radius of curvature. So, now taking all this, Moses derived this expression, this plot, and we will see that we can use it, and Moses actually did lots of theoretical derivations and calculations and in very detail, and that has been used by fracture mechanicians, adhesion scientists a lot, but we are considering only a small aspect of it. We are not going to any very detail that these research papers that actually are written, or research work that has been written, okay, that has been done based on this particular model by Moses. So, here there is a problem. So, let us consider a spherical LDP particle of elastic modulus 0.1 gigapascal, Poisson ratio is 0.45, radius r 2 micron, is contacted with a rigid flat substrate. The work of adhesion between the adherent materials is 100 millijoule per meter square. Estimate the parameter lambda proposed by Moses to understand if DMT or JKR model will be more applicable for understanding adhesion in this case. The critical separation distance between the adherents can be taken as 10 nanometer. So, here you see we can do this exercise by using this Tabor's parameter as well, but this problem has asked us to do find out this lambda, we will do that. So, lambda has an expression that has been given, we need to find out the E star. So, let us say let us do it first. So, this is E by 1 minus sigma square. So, that is 0.1 into 10 to the power 9 Pascal divided by 1 minus this is 0.45, okay, whole square. So, one is to see what this value comes out to be. So, this value comes out to be 0.119 GPa. So, 0.119 GPa, okay, and then one is to calculate this quantity capital K. So, that is 4 E star by 3. So, that is 4 by 3 into 0.119, this is GPa. So, that is equal to 0.159 GPa, right. Okay. What else I need to find out? So, in this model this is 2 sigma 0 by pi WA k square by r 1 by 3. So, let us write this, this is lambda is equal to 2 sigma 0 by this is pi WA k square by r, WA k square by r to the power 1 upon 3. Now, here this sigma 0 has not been given, what is given is delta c. So, how to find sigma 0? Now, I have told you that Mojis essentially use the Dugdale model, in which case that delta c as the delta separation distance between these two surfaces increases, the sigma remains constant at sigma 0, and the area under this curve is basically the work of adhesion, that is W A. So, that is as per this Dugdale model. So, Mojis had used this. So, therefore, W A is equal to sigma 0 into delta c, and this gives rise to sigma 0 is equal to W A by delta c. So, that is equal to here 100 millijoule per meter square 10 to the power minus 3 here, and delta c 10 nanometer 10 to the power minus 9, this is Newton per meter square, that is the way it should be. So, here it comes out to be 10 to the power 9 here, 10 to the power 6 here, 10 here. So, 10 into 10 to the power 6. So, 10 to the power 7 basically Newton per meter square. Yeah. Oh, I have actually changed this quantity here, 45 micron. Okay, let us do it for 45 nanometer. Okay, I think later on I have changed it when I had made this. So, let us take it not 10 but 2.22 10 to the power 6. Okay. So, I think when I was making this problem, I made it to be 45 nanometer, does not matter, we can do it for 10 nanometer also, but I think I wanted to demonstrate certain values. So, here 2 sigma 0, so it is 2 into sigma 0 was how much I calculated, 2.22 megapascal, 2.22 into 10 to the power 6, and here this is pi into 100 millijoule into 10 to the power minus 3 into capital K, that is 0.15 into 9 into 10 to the power 9, this is square divided by R. R was how much, 2 micron. So, this is 2 micron, 2 into 10 to the power minus 6, okay, 1 to the power 1 by 3. So, that is it. So, here we need to use your calculator and you can find out. So, here this value comes out to be 4.44 by 10 to the power 6 divided by this is 1.584 10 to the power 7. So, the whole thing comes out to be 0.28. So, let us say 0.28. So, see, if I had taken it to be 10 instead of 2.2, that mistake that I said, this will be about 5 times more than that. So, about let us say 2.5 or something like that, 5 times 2, no, about 1.25, 1.3 or like that. So, really does not matter, but anyway. So, now this with this value of lambda, what we can see is that for DMT lambda will be equal to 0, because there is no attraction outside this contact area. So, sigma 0 is effectively 0. So, that corresponds to this DMT model, lambda is equal to 0, and as we increase it at a very high value, then lambda goes to very high. So, that goes JKR, but what we have is 0.28. So, 0.28 is in between somewhere here. Okay. So, that makes that this is not exactly DMT and this is not JKR. So, this is an intermediate state, and that intermediate state where lambda is equal to 0.28, and we can actually find out that at a given load P here, okay, compressive load, what will be the area of contact, that we can find out. So, let us estimate also the Tabor's parameter here, that whether this Tabor's parameter and this Mojis's parameter, both of them give rise to the same conclusion or not. I think that is the idea. So, the range of action of surface forces is 5 nanometer here. So, this is equal to 1 upon 5 into 10 to the power minus 9, and this is R is 2 micron. So, 2 into 10 to the power minus 6, work of adhesion is 100 millijoule 10 to the power minus 3 here square, and E star square. So, this is 0.1 not 119, 159, I think 159, 159. So, it should be 159, 0.159 gigapascal, gigapascal 10 to the power 9, and this is square here and whole to the power 1 upon 3. So, this quantity again you please find out using your calculator, and once you do that you find it to be about 2.24, but I think I took it 1.9. So, there is little wrong there. So, this value may be little large, little smaller than that, but it will be close to 2.24 or 2.2 or something like that. So, what it says is that again what you see is that this mu t, okay, is just larger than 1. Okay. So, JKR theory is of course not applicable, okay, and DMT model is also not applicable. So, what we have is an intermediate case. Now, Tabor did not provide this intermediate, Tabor solution was not for intermediate case, and this is the Mojis solution that gives this intermediate solution. So, what we can say is that yes, Tabor's theory or Tabor's parameter and the mod parameter that is deduced by Mojis, both of them give the same solution, that is, it is an intermediate state. So, now let us say the particle is subjected to 150 microgram of compressive load, and let us estimate the radius of contact area when the substrate with the substrate that is attained. So, that we will use now the Mojis curve. So, m is equal to 150 microgram. So, 150 microgram is 10 to the power minus 6 gram. So, that is minus 150 10 to the minus 9 kg, that is okay. And then the p load will be equal to multiplied by 10, that is the acceleration due to gravity. I have taken 10, and that is about 1.5 10 to the power minus 6 Newton. Now, we need to make the get this non-dimensional quantity. So, the non-dimensional quantity comes out to be p by pi w a into r, that is easy to get, and if you find it, it will come out to be 2.387. So, this is the dimensionless load that we estimate from this calculation. And then we can go back to this plot over here, and here this is close to 2.4. So, 2.1, 2, 3 and 4 here. So, this is 2.4, and you can draw a line over here 2.4. Now, how much? Now, when this is 0.28. So, this 0.28 is somewhere here 0.3. So, this curve will be come out to be about 0.3, let us say, and then this is the quantity here, and from there you draw this line that is parallel to here. So, this is this line over here. So, here close to here. So, this is about 1.1, 2, 3, 4, 5, 6, 7, close to at 1.8 or between 1.7 and 1.8, and here it is about 1.8 I found, okay. So, which is good. So, now we have this dimensionless radius of contact, A is equal to this. So, A can be found out as 1.8 into, let us say this is pi into this is 100 millijoule, and this is 2 micron 10 to the power minus 6 to the power square, and this is K was capital K, that was 0.159 GPa 10 to the power 9 and to the power 1 upon 3, that is the way. So, this is in meter by the way. So, what we get is finally 3.36 10 to the power minus 8, so 360 nanometer. So, the contact radius will be about 360 nanometer under this particular load, right, that is the way. So, this is the way one can actually find out, use this Mojis this theory to estimate the radius of the contact that will be formed. Now, there is another problem here. So, tip of an AFM can be approximated as a sphere of radius 50 nanometer, Young's modulus E1 0.1 GPa gigapascal, and then Poisson ratio 0.23, which is brought into contact with a flat PDMS substrate of modulus 2 megapascal, sigma 2, this is 0.5, and then the work of adhesion between the tip material and the substrate is again I have taken to be 100 millijoule per meter square, and the critical interfacial stress, okay, that the interface can resist is 2 megapascal. Determine if JKR model or the DMT model will be appropriate to obtain the pool of load in the above problem and obtain also the pool of load. So, here remember we need to find out the E star. So, we can find it out by this, if we have done it several times over here, and it comes out to be 10 to the minus 9, 9.5 10 to the minus 9 here, 0.38 10 to the minus 6 here. So, this is Pascal. So, the whole thing is 0.3844. This is actually Pascal inverse, I should say, Pascal inverse, Pascal inverse. So, therefore, E star is equal to 2.6 megapascal, Pascal inverse here, okay. So, 2.6 megapascal. Now, let us estimate the Tabor parameter. So, Tabor parameter will be estimated by using epsilon is equal to 5 nanometer. Remember, this is 5 to 10 nanometer or like that, or maybe little larger also you can take, but this is not like 1 micron or 2 micron, no, it is not like that, or 100 nanometer also too large. So, 5 to 10 nanometer is fine to take epsilon, Now, mu t, that is the Tabor's parameter 1 by epsilon. So, 5 nanometer here, and this is R, and work of adhesion elastic modulus is star square I have taken. Okay. So, it comes out to be 8.395. So, it is definitely not DMT model. It is also not JKR model, because this mu t, the Tabor parameter, does not come out to be much greater than 1, it is somewhat greater than 1. So, it is again this intermediate case. So, we estimate the Mohs parameter. So, Mohs parameter we want to estimate. So, let us say sigma 0 is 2 megapascal into 2 into 10 to the power 6, and here it is pi 100 10 to the power minus 3, and k is 4 star by 3. I have calculated to be k will be 4 into 2.6 divided by 3 megapascal. So, I have to see what this value is, 1 point, whatever it is, and R is 50 nanometer, 15 to 10 to the power minus 9, and this is k value. So, I have used the not k value, but I have done the recalculation over here. So, it comes out to be something like this. So, anyway, so you can put the k value, let me write it like this, but you can write k as 4 star by 3 and finally do the exercise. So, whatever it comes out. So, here this is the final thing. So, lambda comes out to be 0.946 or about let us say 1, that is it comes out. So, here everything has been done properly. So, so it is fine. So, lambda comes out to be 0.946 or equal to 1. So, let us go back to this Mohs as this curve. So, here what we have is lambda equal to 1. So, lambda equal to 1, and we want to find out. So, this is basically this intermediate case, highly intermediate case, right. This is the intermediate case, right. So, we can conclude from both Tabor's parameter and also this Mohs parameter, this is an intermediate, it is neither DMT nor JKR. Now, what is the pull off load? So, pull off load calculation, what we will do is, now you see that as the load is been decreased, so from compressive to here it is compressive, and this side it is pull off, negative load. So, negative load means pulled off. So, contact area decreases, and there is a kind of instability here as which, okay. Now, for this case, for lambda equal to 1 is this case. So, this case you see that it goes to over here. So, somewhere here. So, the pull off load will be that when it here the load decreases to this negative value, okay. So, this these portions will not be attained in experiments, okay. So, what you will see in this portion is that this contact will jump off and it will come out of the contact, okay, from the surface. So, it will be this load here, this point here. So, this is the pull off load for this particular case, we can say. So, this pull off load, okay, whatever it is, it comes out to minus 1, minus 1.2, 3, 4, 5, 6, close to 1.8 or so. 1.6, that is fine, 1.6, yeah, right, 1.6. So, this is PW, so this is the dimensionless quantity, comes out to be minus 1.6, finally, it comes to be 25 nanonewton. So, it is at about 25 nanonewton that this AFM tip will come out of this PDMS surface, that is what it means. Okay. So, as we say that there are several areas in which the DMT model will be useful in contact mechanics or in adhesion. See, in the case of adhesion, normally we will deal with soft materials. So, normally we tend to use this JKR, but there are also many applications like this AFM, adhesion of AFM on a substrate, adhesion between two tiny objects, or like adhesion in particle adhesion, particle adhesion for example, okay, where R is very small. There also the applicability of this DMT model increases. Interfacial adhesion between different phases in a nanocomposite, where the particles are there, okay, embedded into the continuous matrix of another material, how these particles, okay, interact or adhere with the continuous matrix, okay. There also it will be very useful. Understanding of thin film coating, because thin film ruptures, okay, because of different adhesive forces, let us say, and there also this DMT model can be very much useful. So, we actually come to the kind of conclusion of a large class of problem in contact mechanics and adhesion, and I will just summarize kind of thing that we did. This list is not exhaustive anyway, but these are the kind of things that we have covered so far in these lectures. Today it is 38 lectures. So, it is like basic concepts I gave about stress analysis, then I considered about contact mechanics on elastic half space. I have described almost all relevant problems, okay, that we need, okay, to understand the adhesion science, and then Hertz contact mechanics I discussed, and then I discussed about some aspects of surface and adhesion energy, because I need to introduce adhesion. So, what is adhesion? It is about surface energy and interfacial energy. So, we discussed that. We also showed that how to estimate these quantities. Then I moved to JKR contact mechanics. I considered both spherical and the elliptical or ellipsoidal geometry, and then I discussed about adhesion of indenters having concave shape. So, in the JKR contact mechanics I used, okay, both the surface energy aspect, surface energy surface mechanics ways of understanding it, and also use fracture mechanics. Okay. I also made use of the understanding from the fracture mechanics, theory of fracture mechanics, to estimate this work of adhesion. Then I discussed about adhesion of indenters having concave shape. Okay. This was like that, concave shape, and I estimated that what will be the pool of load in different cases, and I estimated also the optimized shape that will give rise to maximum pool of load. Okay, that I did. I briefly described about Dugdale-Barenblatt model. I did it because there is more of like fracture. People who are interested in fracture mechanics can read this the topics more detail. And adhesion between rigid spheres I discussed, and finally I discussed about this DMT model. Okay, and I showed that the JKR and DMT model gives the conflicting results, and that was taken care of by this parameter known as the Tabor's parameter, and that contradiction was taken care of. Now, Mojis provide this crossover from the DMT to the JKR model, and we have solved some problems also. So, whatever I have covered so far, okay, is an important aspects of adhesion, but I must say that, okay, if you are interested, I have given also the references, okay, of these different topics. Please read them, and I hope you understand and solve the problems. So far so good. So, what we will do now, we will actually cross over to another kind of problem in adhesion, and this is about the thin adhesive film. So far remember that I was more concerned about an elastic half space. So, it was about two elastic half space essentially which were brought in contact. Now, the size effects are being taken into consideration, and here I have got an adhesive that is actually sandwiched between two plates. The plates can be parallel, they can be rigid, they can be flexible. So, we will take up this problem one by one. So, this adhesive may be strongly bonded to both the substrates or both the films or both the plates, or maybe it is under no slip contact or frictionless contact, and so on and so forth. There are adhesive material can be incompressible, can be compressible. Okay. They may be in this rectangular or plane strain geometry, or maybe in circular geometry, or in symmetric circular theta symmetric geometry and all that, and the equations need to be developed and understood, and you must imagine that this quantity thickness of this adhesive that will be there, and that will come into the picture. So, we will now concern with this kind of problems for next few lectures. That will be the thing. So, here to begin with, we have this rigid plate and this rigid plate, and in between there is this elastic film. So, see, in many practical situations the elastic film, it may not be that adhesive, may not be an elastic, it may be an viscoelastic film. Okay. But for my case, from our derivation here, to keep things simple, we will consider it to be an elastic and not an viscoelastic or poroelastic or plastic. No, we will not consider that, we will consider it an elastic. And this kind of problems are relevant for many practical situations. So, for example, here we have got a dielectric that is sandwiched between this circuit copper layer and this PCB basically design, okay, aluminum layer, and then this adhesive layer, okay, that remains in between bonding them. So, that is a important situation, okay, in where an adhesive remains sandwiched between these parallel plates. So, the adhesion between these two plates, okay, by this thin layer of glue, that becomes important. Similarly, let us say this projectile, okay, which is goes inside, okay, which is basically a bullet, okay, that that needs to that goes into this material, now which is used for protecting bulletproof jackets, for example, where we have got this adhesive layer and then we have got this ceramic tile and metallic plate and like that. So, here also this is of course a kind of impact, okay, impact problem, but nevertheless that there is a thin layer of glue or adhesive, okay, which has a very important role to play, which may not be completely elastic in this case, because what we need in this case of bulletproof situation is a huge viscoelastic dissipation, but nevertheless this is also a thin layer which remains which actually is used over here. Then we have got many other situations, adhesive bonding, where we have, let us say an adhesive between layer between two parallel plates, and there is adhesive failure that occurs either at the one of the interface or in between this adhesive material itself or at the substrate. Now, it may happen that the adhesive is so strongly bonded between these two materials that the cohesive fracture failure occurs. Now, the cohesive failure may happen either in the adhesive material itself or may happen in the substrate also, because substrate may not be very hard in many situations. So, there are all kinds of problems that may be there. So, whatever I am going to say is useful for all these cases, and we will like to now we will like to consider the simpler situation in which we have this parallel plate and within this we have this elastic adhesive film. Okay. So, I will stop here today and I will start discussing about this particular problem in detail in the next lecture. Thank you.